Hello, and congratulations on being selected for the 2018 Microgravity University for Educators, or MgUE, as we'll call it for the rest of the time, because that is so much easier to say. My name is Stephen Smith, and I am here to do your professional development. This is going to be asynchronous online, so you can do it at your leisure during whatever time works best for you. To get us started today, I'm going to bring in my good friend Mike McGlone, who is going to tell you a little bit about what the Microgravity University for Educators is, and tell you a little bit about where you'll be working during your time here at Johnson Space Center. So this is my wonderful friend Mike McGlone. Thank you for joining me.
Morning, Stephen.
So can you give us just an overview of the program? Tell us what MgUE is.
You bet. And again, I'd like to add my congratulations to the teams that have been selected. But Microgravity University is a STEM challenge. It's an opportunity for students working under the guidance of their educators, teachers, or whatever group they're working with, and also working with a NASA mentor, to design and build a satellite launching experimental device, is what we're calling, or SLED. And then they get a chance to bring that device here to Johnson Space Center and test it out on the precision air-bearing floor.
Wow, so that's a lot of acronyms.
A whole lot of
we have a little picture here of the precision air-bearing floor. Can you tell us what we're seeing there?
This is the direct overhead view of the precision air-bearing floor, or PABF, as you'll hear us refer to it. Looking down the bottom of the screen is the back of the PABF, and on the upper part of the screen is where the testing platform is at, where people can stand while they're watching the operations. And during the event, is this a video, Stephen?
It's not. This is just a still photograph.
So basically what the precision air-bearing floor is, you can see there, it's a large steel plate. The devices that sit on it, sleds, there's a air chair, as it's called. Actually, air is pumped down into pads resting on the steel plate, push air down, which lifts whatever object is sitting on the precision air-bearing floor. If you're familiar with an air hockey table, which used to be a popular game, it is kind of reverse air hockey in terms of the puck would be pushing air down to slide around instead of the other way around. So it's a very neat piece of equipment, and we get the opportunity to use it to do our testing for MgUE.
Cool. Now this PABF is in Building 9, which is a really cool facility, and we actually have some video of the facility itself. Would you mind walking us through that?
You bet. So as we refer to Building 9, which is also known as the Space Vehicle Mock-Up Facility, is a very large hangar-like building. You see a view here from one of the catwalks looking out over some of the facilities that we have within Building 9. It is designed basically to hold full-scale models that are used for a variety of tasks. What you're looking at right now are several of the models of the modules for the International Space Station, or ISS. We're coming up to see some of the Russian segments here. These are used for training for astronauts, also used by engineers for testing procedures or equipment. There's a number of areas that are constantly being worked on, be it the environmental systems or emergency procedures, any number of things that they use these for training. And we'll be working in a small area of this. You see it coming up, opening up just behind that module right there is the precision air-bearing floor, that black area just across. We'll be working in teams down below that in that open area, and we also just went past the partial gravity simulator, or POGO, which some folks may get an opportunity to experience as well. You see here a few more modules from the International Space Station. There's actually one we just missed, which is a space shuttle mock-up that is still in the building, although most of those have been removed. You see across the floor now is the Orion mock-up that's used for training for that next stage of crewed exploration of space. The commercial crew mock-up right there in front of us. And then at the far end of the building is the robotics division. So you see some of the robotics that are on display there, some of the SEVs. I see a spider knot down there. There's
the Canada arm there too.
Yeah, the Canadarm, that's an interesting artifact. It's from the space shuttle days and still sits there. Not used anymore, but it was used for training at one time, but it is there. We see, again, there's Robonaut, I believe, and some of the other work that the Robotics Division does. And hopefully we'll get a chance, those that are here at MgUE, since we're not on the PABF all the time, get a chance to see some of these other areas of Building 9.
Very cool. Well, thank you so much for your time, and I appreciate you. So this is the guy who's kind of running it all for MgUE. So he's going to pass it off to me here to do your professional development, and then in the end, I'll pass it back to him, and then you'll be at his mercy.
Well, again, congratulations to the teams, and Stephen, enjoy the professional development part.
Absolutely. Thank you, Mike. Appreciate it. Okay, so now I'm going to talk a little bit about the engineering design process. So the work that you're going to be doing is an engineering design challenge, and we're encouraging you to use these a lot with your students as well. So as we do that, I wanted to talk a little bit about what the engineering design process is. Now you'll notice this looks very similar to the scientific method, for example. And just like the scientific method, there isn't just one. There isn't just one process, so it's really hard to say, to teach this in a, what's step one, what's step two, what's step three, because it's fluid. It sort of depends on the work that you're doing. And you'll notice that they both have a circular design. So just like in the scientific method, you have your observations, then you make your hypothesis, and you work through your experiment itself. And then at the end of your experiment, you have your conclusions, which leads you, of course, to more questions. And then you'll start the process all over again. The engineering design challenge, or the engineering design process, is the same way. However, we tend to teach in a linear fashion. So instead of allowing them to make mistakes and letting them come back, you basically want them to follow your explicit instructions and then create the model that you designed. And I'm here, I want to express to you that I think that that's the wrong way to do engineering design. There's a philosopher, Antoine, and I'm not going to try to say the last name. I will butcher it, but there it is. It's French, and so I could just make some really haughty noises, and I'm sure it would sound about right. But he basically said that if you want to build a ship, you don't drum up people to collect wood, and you don't assign them tasks and work, but rather you teach them to long for the endless immensity of the sea. Now that's a very flowery way of saying that if you want people, for example, to come up with a great biological engineering something, you just teach them to love biology, and then they will find a way to do that thing. If I just teach you or tell you how to build the ship that I've always built, I'm going to get the ship that I've always gotten. But the only way that we move forward is if we let them fail. We let them go beyond. Talking about failure, there was a TED Talk, and a scientist, Alejandro Sanchez Alvarado, I don't think I'm supposed to roll that particular R because there's only one, but it sounds cooler if I do it that way. He said, if you don't feel ignorant most of the time, you aren't sciencing hard enough. I like two things about this. The first is we tend to coddle too much, hold hands too much, and we're afraid to let our kids fail, and we're afraid to let them see what that's like. But also, he used science as a verb, which I am a firm believer that science should be a verb and not a noun. So when we teach science as a noun, or as a set of facts, or even more importantly, a set of dates that some white guy figured out that fact, we're not teaching science. So don't be afraid to leave your challenges open-ended. So you give them an end goal. You want this design to do X, whatever that thing is, but let them figure out how to get there. Give them constraints, because engineering is always done in the real world and has constraints. But leave the challenge open-ended and let them figure out how to meet your challenge, even if it's in a way that you didn't figure out before or haven't thought of yourself. Because what we're trying to inspire in our students is ingenuity. And what is that? What is ingenuity? There's a really interesting example instead of just a definition. So walking across an empty room requires very little ingenuity. However, if that room is full of snakes, hungry bears, and landmines, the ingenuity requirement will have gone up considerably. And as we all know, the world that we are sending our students into is full of snakes, hungry bears, and landmines. So we want to give them, you might also think about this as critical thinking. that sort of scientific thinking where they can get a new or novel problem and figure a way around it, and maybe in a way that no one's ever done before, because some of the problems that our students are going to see are involving things that have never happened before. They're going to be working with technologies we've not even dreamed of. It's also important to note that this is not a competition. Your design and the design of your students when you do engineering design process challenges, it's not a competition. The important thing is the process, for them to learn how to go from point A to point B. And some ways to do that, if it was a competition, and allowing the students to look at each other's works would be horrible, because they would cheat off each other, right? And we think about that all the time in class, that we don't want them to look off each other's papers and that sort of thing. But there is no one way to achieve a goal. And sometimes the students over here have worked through in a way that inspires this other student over here to work maybe even another way. They see a problem that this group has, and they can solve it, and they can help each other. Because again, the end goal is for each team to have a design, and each team to make it to figure out how to solve that challenge. And it doesn't matter who gets there first. There's not a best way to do it necessarily. And the same is true for you guys here at MgUE. When you come here, we're not competing one team against another. There's no prize at the end. The prize has already happened. The prize was you being selected to come here. So we want you to think about this as a challenge, but not a competition. And we want you to work together with your mentor and with each other. So what's next? The rest of this PD, the rest of this part one is on our badging system. And you'll find that at our Texas State website, which you will have already had because that's where this video lives. The badging system is a good way for us to keep up with the work that you're doing. And it's a good way for you to be able to work this on your own time. And there are other badges on there that my group, the EPDC, Educator Professional Development Collaborative, has on there, and we're going to be adding to that badging system that you can continue your PD later on. So the next step for you is to look and find out what your first assignment is. Do that assignment, turn it in, and then we'll see you in PD number 2. I thank you so much for your time.